Section 4.11, equilibrium application of Newton's laws of motion. So this is where we're going to start pulling everything together, this section and the next section. And this is what the meat of this chapter. I know we've seen a lot, but it's going to be nice to bring it together. So first, our definition of equilibrium, since that's right off in the title. An object is in equilibrium when it has zero acceleration. If there's zero acceleration, we know that there's, by Newton's second law, that means there's no net force acting on it, because sum of the forces is equal, or the net force is equal to the mass times the acceleration. So zero acceleration means that the sum of the forces has to be equal to zero. If there's no net force acting on an object, that tells us that the velocity is going to be constant. So it might mean that there's no velocity, that the object's not moving. It can also mean that the object is moving at a constant speed in a straight line. But either way, equilibrium, zero acceleration, and the sum of the forces, or the net force in both the x and the y direction, must be equal to zero. So that's something you want to pay attention to. If it mentions equilibrium, that, boom, keys you into zero acceleration. So let's look at a reasoning strategy for solving these problems. First step, we want to select the object or the objects to which the equations of equilibrium are to be applied. Like, okay, I want to focus in on this raft, or I want to focus in on the book, or on the ball, or maybe the book with the ball on top of it. Then we want to draw a free body diagram for each object chosen above. So maybe you have multiple objects, you can draw a free body diagram for each of them. And on the object, not forces exerts on its environment. So this is just saying, okay, what does the ball experience, not how does the ball exert a force on the world around it. Then choose a set of x and y axes for each object and resolve forces in the free body diagram into components that point along these axes. Note, when you choose your axes, they don't have to be side to side and up and down. As we saw in the ramp example, we can choose them to line up with an angled scenario. We'll see an example of that in just a moment. Then we want to make sure whatever we choose for axes that we're able to resolve all ones that point along them. So usually we'll try to set our axes that they line up with the most number of forces. Finally, we'll apply our equations of equilibrium, Newton's laws, and solve for the unknown quantities. Okay, sounds straightforward enough, so let's give it a go. So here the figure shows a traction device used with a foot injury. The weight of the 2.2 kilogram object creates tension in the rope that passes around the pulleys. Therefore, tension forces T1 and T2 are applied to the pulley on the foot. The foot pulley is kept in equilibrium because the foot applies a force F to it. This force arises in reaction, Newton's third law, to the pulling effects of the forces T1 and T2. Ignoring the weight of the foot, find the magnitude of F. All right, so here we have a problem, and they very kindly gave us a picture in this one where they drew in the directions of T1 and T2 and F. So we're going to focus in on the forces that are experienced by this foot, right? That the, or really this pulley, that the pulley in the middle, that there's this tension, T1 and T2 pulling, as well as the foot pulling on this midpoint. So this means now that we've identified these forces, we want to make it into a free body diagram. So we're going to take these three forces and also try to draw an x and a y axis with them. Now, how do we want to draw the x and the y axis? This is a great question, point of interest, right? We want to line it up with at least one of the forces. If we just draw it purely horizontally and vertically, we're not going to line it up with any of them, right? None of the forces will align with that. So that's not ideal. We could line it up with T1 or T2, but then we'd have to figure out the angle that F makes with the others, and we do need to keep them perpendicular to each other. So when I keep these two perpendicular to each other, even if I line up with T1, it's not going to line up with T2. It's going to miss it every time. So what I'm going to suggest instead that we do, especially with how they defined these angles relative to this dotted dashed line that's opposite the foot force, is that we instead line up our axes with that foot force. So line up the horizontal with that and make the vertical at an angle like so. So I'm going to encourage you to do that, to draw in the x and the y axes, and then to follow the second step of resolving all of the forces into components that point along either the x direction, as it is shown, or along the y direction. So go ahead and see how you do with that. So go ahead and pause the video now. All right, did you do it? I'm hoping so. Well, let's take a look and compare notes. So here we have our free body diagram with the positive x direction, the positive y direction shown. That's very nice, clear there. And then we have the three forces that are all pulling on that point in the center. So that looks good there. And then force F is already purely in the negative x direction, so we don't need to do anything with that one. But T1 and T2, we're gonna have to break down into x and y components, right? So we'll use cosine of 35 to get the x component, so that will give us T1 sub x, and we'll get the y component with sine, so that would be T1 sub y. Similarly for T2, we could have the cosine to get us the x component, and sine to get us the y component of T2. So those are really useful things to identify. I'm happy to talk you through that if you're at all uncertain. Once we have it in terms of the x and y components, now we can go back to our standard summing up the forces in the x direction and summing up the forces in the y direction. And because this is equilibrium, because it says that this isn't moving, that tells us about the acceleration. What is the acceleration in both the x and the y direction? It has to be equal to 0. There's no acceleration, so there's no net force acting on the system. The foot is stationary. It is going to stay there. Alrighty, so with these things in mind, we can then sum up the forces in the x direction as well as in the y direction, and we'll be good to go. So let's take a look here. So in the x direction, we would have, excuse me, the positive T1 cosine of 35 plus T2 cosine 35. Those are both in the positive direction. Positive, positive, and then there'd be minus F because that is in the negative direction, right? So we won't have to worry about that so much. Now, what about the y direction? Well, for the y direction, we don't have to worry about the force F at all. It's just going to be T1 and T2. We do have to be careful with sign here because T1 is going in the positive y direction, but T2, notice, is going in the negative y direction. So that's why we would need to add then a negative sign for when we sum up the forces in the y direction. So there is indeed this negative sign goes into summing up the forces because T2 is acting in the opposite direction in terms of y components. All right, so if we go to solve, we could start with this top one. I could add T2 sine of 35 to the other side. So I'd have T1, excuse me there. T1 sine of 35 is just equal to T2 sine of 35. So the sine of 35 is the same on both sides. What does that mean? Well, that means we could divide by sine of 35 on either side and it will just go away, right? We don't have to worry about that. And so this tells us then that T1 is equal to T2. In other words, that the tension is the same throughout the rope. And this will generally be the case. As long as it's one distinctive rope, you can just call the tension T. So that's a really useful side note. But it was also nice that we could affirm that here. The y direction, perhaps not as useful, but still affirmed what we may have known but forgotten. What about the x direction? Well, now that we know that T1 and T2 can just be called T, we have two of the same term here. So we could rewrite this as 2 times the tension in the rope times cosine of 35. If I just write that T1 is equal to T and T2 is equal to T, and this is minus F is equal to 0. So this tells us that the force F is then just equal, if I add it to either side, to 2 times the tension T times cosine of 35 degrees. Cool. So we've now arrived at an expression for our force that the foot must apply. It still is in terms of a T, which is a little bit uncomfortable. So if we want to solve it, we can do it. We'll just have to take this one step further. And that's noting that the tension in the rope is also going to be the same tension that's supporting this 2 kilogram weight or block. So if the tension's pulling up, and that's the same tension as T2, then that has to be equal to the 2.2 kilograms pulling down. So we could do a free body diagram just for that block, and we get T going up and mg as the weight going down. And because it's in equilibrium, we would see that the tension is equal in this instance to mg. And this tension is the same as T1 and T2, so we could just substitute in mg over into our expression for F. So we would, in summary, we would get that we would have 2 times the 2.2 kilograms, can write this out, times g, which is our 9.8. Again, keeping that positive, meters per second squared. So that's our 2 mg, and then times cosine of 35. Sorry, the cosine there got a little messy, but hopefully you can still see. And so if you calculate this, you should find that it comes out to, interestingly, a 35. And what would our units be? The units of force. They are indeed newtons. So, lengthy example there, but the key is that we identified that this was an equilibrium problem, so that the sum of the forces in both the x and the y direction had to sum up to 0. That pulls us through this. The next section we'll be looking at non-equilibrium applications of Newton's laws of motion. So stay tuned, it's going to get even more exciting. Things are picking up and we're pushing hard to get to the finish.